Now let's take a minute, look at some basic properties of the derivative. Now I've already in a previous video looked at the power rule. We said, okay, if you have f of x equals x to the alpha, where alpha is a real number, then f prime of x, meaning the derivative, is equal to alpha x to the alpha minus 1. So this is one of the properties that we've looked at. Well, we're going to look at some others, and before I do that, I want to introduce you to some different kinds of notation. This right here is prime notation. This is how we denote the derivative. But let's look at some others. Let's suppose that we've got this y equals f of x, of course, equals x to the alpha. F of x and y, they're interchangeable. There is this thing called the Leibniz notation, okay, that we could use. Now, Leibniz was a famous mathematician back contemporary with Newton. He gave us a lot of what we know about the calculus. And Leibniz notation, whereas we have prime notation here, Leibniz notation might do this. It would go like this. It would go dy over dx. It's kind of puts you in mind of the slope, the change in y over the change in x. That's kind of what it puts you in mind of, but it's just a notation, and it reads like this: the derivative of y with respect to x. That's the way we would view this. We're taking the derivative of y with respect to x. In other words, x is the independent variable, and it's the same as f prime of x. Okay? So we might say dy dx for this function up here would be alpha x to the alpha minus 1. Now we don't have to do it that way. We don't have to say dy dx. Y is equal to x to the alpha, so we might do it this way. We might say d dx and just put the x to the alpha there. And that means the derivative of this thing with respect to x. The derivative of x to the alpha with respect to x. So we might see it that way. But the thing is, you'll see the derivative written different ways. You might even see y prime. You might see dy dx. Okay? Of course, you might see f prime of x. And of course, dy, whoops, I've already said dy dx. Sometimes you'll see this. You'll see a capital D with a little x there. That means the derivative, and this tells you with respect to what? With respect to x. So anyway, these are some notations. And, you use, depending on what's the easiest for you at the time, that's probably what you'll use. But, so first of all, we have this property, this power rule property. Now, there are some other properties. Here's one property. If you want the derivative of a function times a constant, okay? Let's suppose we want the derivative of this function, but it's not just the function, it's times a constant. What we can do is we can just factor out that constant. In other words, you could just multiply the constant times the derivative. The constant is something that can be factored out. Then you go in and do the, work on the derivative and then multiply the constant at the end. So, for example, let's suppose that you have this situation here. Let's suppose that you have 7x to the 9th, like that. Now, you have this little power function here, but you have the constant in front. Well, what I'm saying is you could factor out that 7 and just set it off to the side and then go ahead and work your problem here. So this is going to be 7 times 9x to the 9 minus 1. See? The power rule. And then, of course, that's just going to be 63x to the 8th. Yeah. Now, you can whenever we're trying to verify these properties, we always go back to the definition. So for example, let's suppose that we want the derivative of this thing, a constant times f of x. Well, look, if we go back to the definition, if we go back to the difference quotient, we've got the limit as h goes to 0 of, let's see here, we're going to have c f of x plus h minus c f of x over h. Now, you can see here that the c can be factored out of the top. And this would be the limit as h goes to 0 of c, here's f of x plus h minus f of x over h. Okay, and now notice this limit. Remember, a limit of the product is the same as the product of the limit, so I could say, well, I'm going to write this as the limit as h goes to 0 of c times the limit as h goes to 0 of this. But the limit as h goes to 0 of c is just c. c doesn't care what h does. So really, I could write this way. And remember, for these limits, we can factor out the constant as well. So we get this. And this is just f prime. So you can see here, this is c f prime of x. So factoring out that constant, which is fine. Okay? So we can factor out a constant and then just differentiate. Now, also, we've got this situation that if we want to take the derivative, let's suppose we've got a couple of functions, f of x plus or minus, let's just throw it all in here together, plus or minus g of x. Well, that's the same as the derivative of the f of x plus or minus the derivative of the g of x. Now let me show that's true. Let me go back to the difference quotient, and let me just look at the derivative of, instead of doing plus or minus, I'll just do the plus, f of x plus g of x, to keep things from looking too messy. Well, if you plug that into the difference quotient, you're going to get the limit as h goes to 0 of, let's see what goes up here, f of x plus h plus g of x plus h, okay, minus the function f plus g, right? See, like that. Because you're thinking of this sum as just one function, It's a combination of f and g. So here we go. There's h down there. Now, I can group things together. So I want to group the f's together and the g's together. Now dig what happens here. I've got the limit as h goes to 0 of f of x plus h minus f of x. See, I'm grouping these together. Plus g of x plus h minus g of x. See, minus all over h. See, look at that. Now, I can group things together further, because notice that I can do this. I'm going to say the limit, okay, as h goes to 0, and I'm going to do this. I'm going to say f of x plus h minus f of x over h. I'm going to kind of separate these, plus the limit as h goes to 0 of g of x plus h minus g of x over h. See, I've not done any harm here. I've just said I'm going to take the limit of this part plus the limit of this part. See, they have the same denominator, so this is exactly the same as this. What I've done down here breaking these up, it's just this. See? In fact, I could add these back together because remember, this is a property of limits that you can do this. Now, this is the difference quotient that gives me the derivative of f. So this is f prime of x plus this one is g prime of x. There we go. So this shows you, now we could do the same thing for the difference, and we could show it's true for plus or minus. So f of x plus or minus g of x. I just showed it for the plus, but it would work either way. Now also, let's look at this. A couple other properties. Remember that if we do have the derivative of a constant, of just a constant, just a number. Now remember, the derivative describes the rate of change. That's what it describes. Well, a constant doesn't change at all, right? And you can see that this is just going to be 0. So we could look at the difference quotient. We could say, well, let's try this with the difference quotient. And what I would have is let's just suppose that f of x equals a constant, and I wanted the derivative of that f of x. Well, it's f of x plus h. Well, f of x is just c minus f of x, c, all over h. So you can see, yeah, it would just be 0. So that's almost, that's pretty trivial. Now, remember also the derivative of a line. Let's suppose we've got mx plus b. Now, remember, the derivative is the slope of the tangent. Well, the slope of a tangent for a line is just the slope of the line. But if we put this in the difference quotient, let's see what that would look like. This would be m times x plus h plus b minus mx plus b all over h. And let's see what this looks like. We've got the limit as h goes to 0 of mx plus mh, see, mh plus b. I just cleared my parentheses, minus mx minus b over h. And some things cancel. And all I'm left with up here is this mh over the h, and that's just m. So you can see that that's another property. So in other words, the derivative of a line is just going to be the slope. Yeah. So there we have some basic properties that enable us to facilitate when we're trying to actually find a derivative. These properties will help us out. So just in summary, let's see what we've got here. We've got the derivative of a constant is 0. The derivative of a line is just, the slope. The derivative of a sum, f plus or minus g, is just going to be f prime plus or minus g prime. And let's see what else. We've got the power rule. We've got the power rule. Yeah. So these are some properties that you can keep in mind as, and this is just kind of a summary of them, that you can keep in mind as you're working. And oh yeah, let me put in the constant property. Yeah, there we go. Just kind of a summary of them.